Dr. Preeti. In this video, I will be discussing about the basics of Opamp, that is operational amplifier. We will see that what are the different stages of operational amplifier and what is their uses and internal structure of different stages of operational amplifier. Then we will study about some basic parameters related to operational amplifier. Operational amplifier is a directly coupled high gain amplifier in which we have the output that is the amplified form of the difference of the input signal. If we are applying two signals at the input side, then the output that we get is the amplified output. That amplified output is the amplified signal based upon the difference of the input signals applied at the input of operational amplifier. There are several applications of operational amplifier. It is used in analog computers. We have ideal operational amplifier and practical operational amplifier. So we can use operational amplifier with feedback and without feedback. Generally, we use operational amplifier with negative feedback because there are several disadvantages of operational amplifier when we use it without feedback into the system. These are the different stages of operational amplifier. At first stage, we have input, that is the input stage. The next is intermediate stage. The third one is level shifting stage. And the last is your output stage, where we are measuring the output from this complete block diagram of the operational amplifier. Here we have two inputs, non-inverting input and inverting input. We can name it as I1 and I2. So these two inputs in non-inverting and inverting inputs, so the output of this complete system that we get here is the amplification of the difference of these two signals that are connected at the inverting and non-inverting terminals of this operational amplifier. At the first stage, that is your input stage, here we have dual input balanced output differential amplifier. So this dual input balanced output differential amplifier we have studied, we have discussed in previous videos that what is the structure, what is the circuit diagram of this dual input balanced output differential amplifier. Dual input indicates that here we are having two inputs, and balanced output indicates that the output that we are measuring is between the two collectors of the differential amplifier. So the first stage, input stage of this operational amplifier is dual input balanced output differential amplifier. At the intermediate stage, we have dual input unbalanced output differential amplifier. Dual input means here also at the second stage, two inputs are present, that is a dual input configuration, but the output that is mentioned here is an unbalanced output. Unbalanced output, that means that we are going to measure output from any one of the collector. For the differential amplifier, we are having two transistors and we can measure output at the collector of both the transistors. So for unbalanced configuration, we will be measuring output from any one of the collector from the two transistors, and the reference potential will be the ground potential. At the third stage, we have level shifting stage. At this stage, we can have a circuit that is used for level shifting, such as emitter follower used in using the constant current source. At the last stage, that is your output stage, we have a complementary symmetry push-pull amplifier, and after that we measure the output of this operational amplifier, and that output will be the amplified version of the difference of the two inputs, that is non-inverting and inverting inputs applied to the input side of this operational amplifier. Opamp is as we discussed that it is a differential amplifier and it will amplify the voltage which is differentially present between the input terminal. It does not amplify a single input or the inputs separately. It just amplifies the difference that is available at the input side of the transistors that are connected at the input of operational amplifier. So, as I discussed about the different stages, the input stage, that input stage is a dual input balanced output differential amplifier. The two inputs are inverting and non-inverting input terminal, and this stage provides most of the voltage gain of the op-amp, and it decides the value of input resistance that any operational amplifier is going to offer. The second one, that is the intermediate stage, is normally another differential amplifier. As I told that it is a dual input unbalanced output configuration type of differential amplifier. The input stage drives the next stage, and the stage is dual input unbalanced output differential amplifier. Then we have the level shifting and output stages as already discussed with the block diagram of operational amplifier. This is the internal structure of this operational amplifier, and this is specifically for IC 741 Opamp. We have different ICs for operational amplifier. So, this circuit is for IC 741 Opamp. Here we have number of bipolar junction transistors that are being used to design this operational amplifier. We can design this Opamp using MOSFET also. Here the circuit is shown that is designed using bipolar junction transistor. Here the two transistors, that is Q12 and Q11, these are providing the reference bias current. These are providing biasing current as a current source, as we discussed in the previous video that how we can design a current source that is going to provide a constant current at the next stage. So, here Q12 we can see here it is the base, emitter and collector. Here also we have base, emitter and collector. So, in both the transistor Q11 and Q12, the base and the collector is tied together. So, here we can see that voltage at the emitter is equal to voltage at the base. But here one thing is that the base current of BJT is not 0. So, here some current will be flowing through the base terminal of this bipolar junction transistors. So, these two transistors are providing bias current to the next stage. Here next stage, here we have transistor Q8, Q9. Q8 here is also connected in diode configuration, because here the base and collector of this transistor is tied together. So, it will also act as a constant current source. Then it is the second stage. Then we have level shifting stage, and at the output we are measuring from the transistor R6 through the resistance R6 and R7. So, this is the internal structure of the different stages of IC 741. This is the separate diagram from the previous figure, that is the output stage. So, this is the circuit diagram of just that part that is representing the output stage. So, here figure A that we have is an emitter follower is a class A output stage that is connected here. The figure B that is showing the class B output stage. And figure C, that is showing the output of class B stage, and the last one is class AB output stage. So we can have different output stages for an operational amplifier, class A, class B, class AB. And here if we observe this output, here we can see that the waveform that we are having here is not continuous. So here some error is there. If we have applied a sinusoidal signal at the input, so output should be your sinusoidal output. But what we are getting is there is some duration on the time axis where we are not getting any output. So this is the problem associated with class B amplifier stages, that it has a distortion into the output stages. So this distortion here is called as crossover distortion. So this crossover distortion can be removed by adding some external voltage at the base of the transistor that will keep the device on, and we can have the signal available in that duration in this figure where we are not getting any output. Different device parameters associated with the operational amplifier for NPN and PNP. The IS current value 10 raised to the power minus 14 in both the case, and beta value will be 500 for NPN and 50 for PNP transistors. Similarly, the parameter ISA we have 0.25 into 10 raised to the power minus 14 ampere, and ISB will be 0.75 into 10 raised to the power minus 14 ampere. In the figure of IC741, the transistors that Q14 and Q20 are assumed to have an area around 3 times that of a standard device. So if we do the DC analysis of operational amplifier, the DC analysis will be in the same manner like we did with the other circuits. We will remove the AC sources of the circuit, and we will write the equations, and solving that we can get the reference current as VCC minus VEB12 minus VEE11 is of transistor 11. Minus and minus time of minus VEE, this is just we can get by writing the KVL equation. So for particular value of VCC and VEE of 15 volts and VBE and VEB12 of taking 0.7, we get I reference at 0.73 milliamperes. In the circuit, the transistor Q11 is biased by the reference, and the voltage developed across is used to bias the transistor Q10, which has a series emitter resistance R4, and this part of circuit here is shown, that is the Weidler current source. Assuming that the beta 10 to be having a larger value, we can write it as VBE11 minus VBE10 is equal to IC10 into R4. So we can say that we can get this value as VT ln I reference by IC10 is equal to IC10 multiplied by resistance R4, where it has been assumed that IS10 is equal to IS11, and substituting the known value of I reference and R4, this equation we can solve by the trial error method to determine the collector current, that is IC10, and for this case the result of IC10 that we get is 19 microamperes. in this circuit diagram, that is the DC analysis of 741 for the input stages. Here we can see that the current that is flowing from Q9 transistor is 2I1 upon 1 plus 2 by beta P, that is the PMOS transistor. So IC1 is equal to IC2 and IE is equal to IE4, that we write as IE. And the base current of transistor Q3 and Q4 are equal with the value of 1 by 1 plus beta P plus 1. So, due to the larger value of beta P, 1 plus beta P can be written as beta P, where beta P denotes beta of PNP device. So, we can express the output current of the mirror as IC is equal to 2I upon 1 plus 2 by beta P. So, we can further write a node equation for node X here. If beta P is greater than 1, then this node equation gives us 2I is nearly equal to IC10. Now, the DC analysis of IC741 input stages that we were seeing is continued here. IC6 is nearly equal to I. So, here we can say IC3 is equal to I, IC4 is equal to I. So, we can neglect the base current of Q7 and we can write that IC5 is nearly equal to current I. The bias current of Q7 can be determined from IC7 is nearly equal to IE8, that is 2I by beta N, and plus VBE6 plus IR2 divided by resistance R3. So, here VBE6 is equal to VT ln I by IS. Input bias and offset current. The input bias current is defined as the average of current from the base of 1 and 2, that is the IB1 plus IB2 by 2. For IC741, we get this IB as 1 upon beta N. I offset is mod of the difference of two currents, that is IB1 minus IB2. Input offset voltage. The base emitter voltage of Q7 is VBE17 is equal to VT ln IC17 by IS, and by putting some particular values we get this as 618 millivolts. The collector current of Q16 can be determined from the equation IC16 is nearly equal to IE16, and that we can write as IB17 plus this term, that is IE17 and multiplied by R8 plus VBE17 divided by R9. So, that all discussion that we have done till now is about the different stages of operational amplifier and its internal structure. Now, for our circuit design purpose, we do not always use the complete block diagram or the internal structure. So, for simplicity, we represent this operational amplifier symbolically, and this figure is showing the schematic symbol of operational amplifier. So, differential amplifier stages of Opamp is designed to be operated in a differential mode. The differential inputs are designed by positive and negative notations. The positive input is the non-inverting input, and the AC signal or the DC voltage applied to this input produces an in phase or the same polarity signal at the output. On the other hand, the negative input or the inverting input is called inverting because an AC signal or the DC voltage that is applied to this input produces an 180-degree out of phase or opposite polarity signal at the output. So here we can see that we represent this operational amplifier by a triangle with the negative and positive inputs. The negative input that is termed as inverting input and the positive one that is termed as non-inverting input. So when we apply input as the inverting terminal, the output is 180-degree out of phase with the input. When we apply input at the non-inverting terminal, then your output will be in same phase with the input. Or if we are applying inputs at both the terminal, then whichever input is dominating, depending upon that, the phase of the output will appear. Here the A that is written inside this triangle is the gain of this operational amplifier. A is the large signal voltage gain which is specified on the data sheet of any operational amplifier. Now this is the complete symbolic representation with power supplies of this operational amplifier. Different pin numbers are pin number 2, 3, 4, 6 and 7. So inverting input will always be connected to pin number 2 of IC 741. Non-inverting input will be connected to pin number 3 for IC 741. The output that we will be measuring is at pin number 6, and the basic and the necessary requirement, that is the supply voltage that will be provided to this Opamp, will be given to pin number 7 and pin number 4. Pin number 7 is for plus VCC and pin number 4 is for minus VEE. So this figure shows the power supply connections for the 741 or 351 Opamp. The numerals adjacent to the terminals are pin numbers, remaining pins are omitted for the simplification. So this is all about the basics of operational amplifier. The further details related to the Opamp that I will be discussing in the next video. Thank you.